In today's lesson, we are going to look at linear regression and in particular start thinking about how we do inference around the slope parameter. So in the last lesson, we saw how do we estimate the parameters of the distribution, and this time we want to see if we can conduct some hypothesis tests or form some confidence intervals. So the two objectives for today are to understand the sampling distribution for the slope parameter, and then we want to use the sampling distribution to test hypotheses or confidence intervals. So again, once we get that sampling distribution down, as we saw in the sections on hypothesis testing and confidence intervals, once we know the sampling distribution, we can apply the same types of procedures we're used to applying. So we'll often have questions of scientific interest, which are going to correspond to tests of the slope parameter, right? So in terms of why do we care about this? Well, if you start to try to frame different scientific questions, often you could think about those as being questions about whether the slope parameter, for instance, is equal to 0 or not. So is there an effect of treatment on the outcome, right? Let's suppose that x, if we zoom in here, x is going to equal to, say, 1 if you get treatment, and it's going to be 0 otherwise, right? And then we say y is going to equal to some baseline outcome plus beta 1 times x plus epsilon, right? Is there an effective treatment? Is the same thing as asking, does beta 1 equal 0, right? And so that's a question that if we could test the hypothesis h naught beta 1 equals 0, then we could ask this question of interest here. In general, if we have sort of the full situation we might care about is going to be the null hypothesis being beta 1 equals to some beta. And this could be, is the effect size at least this large, for instance, right? But beta 1 equals 0 is going to be a very common test. And it's essentially the test of, is x linearly related to y? Right? So as we've seen repeatedly, in order to test hypotheses, what we need to do is first work out what the sampling distribution is. Okay. Now, we can show that the expected value of beta 1 is going to be equal to beta 1, assuming that we have a correctly specified model. We can also show that the variance of beta 1 is going to be given by sigma squared, which is the variance of our epsilon, divided by sxx, which is going to be the squared deviation. I think actually throughout the term, mostly we've been using sx instead, but both of these notations come up frequently. So if we assume normality, then beta 1 hat is going to be the combination of normally distributed random variables. And any combination of independent normally distributed random variables is also going to be normally distributed, right? And so if we assume normality, then what we're going to get is that beta 1 will follow, or beta 1 hat is going to follow a normal distribution with mean beta 1 and variance sigma squared over the squared deviations of x, right? And of course, if that sampling distribution is normally distributed, then we can use the normal hypothesis test, normal confidence intervals, right? So we would get this approximate sampling distribution here. Whenever sigma squared is not known, we can replace it with s squared, and s squared is going to be our estimate of that variance. We saw how to get the estimate of the variance when we were looking at that variance breakdown, right? So if you take the sum of squared errors, you divide by n minus 2, that's going to estimate sigma squared, right? And so we can define the test statistic to be beta hat 1 minus beta 1 divided by s, which we just talked about how we would get to, divided by the square root of the squared deviations here. And under normality assumptions, if we're assuming that the population is normally distributed, then this is going to follow a t-distribution with n minus 2 degrees of freedom. Now, again, I'll point out that we're using an n minus 2, not an n minus 1 t-distribution here, and that's because we've estimated two different things, right? We estimated the intercept, we estimated the slope. And so you take away the number of things that you've estimated. And then using this sampling distribution, we can just use the t-distribution as we have in every other t-test, right? So we can form confidence intervals or we can form hypothesis tests using this sampling distribution here. And that's basically as simple as it is, right? So we think about our t-statistic. This t-statistic looks no different than what we would have in any other t-statistic. And the idea is that when we're taking, if we have the null hypothesis that beta 1 equals some value beta, then under the null distribution, we'll have beta 1 minus beta, right? And these two are going to correspond to each other. And we'll divide this by s over the square root of sx, right? And this is going to follow a t n minus 2. And so then we can either take beta 1 plus or minus sort of the t alpha over 2 n minus 2 times by our variance here, right? Or we can use this to compute our p-value, where once again we'll be looking at some t-distribution here. We'll have, say, our value and then the upper tail, our value, and then the lower tail. Of course, you can do a two-sided or a one-sided test as well, right? And so the processes that we get after we use the sampling distribution here are going to be exactly the same as the ones that we've been looking at throughout the latter part of this term. So the sampling distribution for the slope parameter is going to be, if we make normality assumptions, we'll follow a t-distribution with n minus 2 degrees of freedom. The sampling distribution can be used to test hypotheses or to form confidence intervals in exactly the same way as we did for the mean. Now, with that, we've sort of touched on everything that we were going to talk about this term. So we've done a very high-level overview of descriptive statistics, of probability, both discrete and continuous. We talked about point estimation. We talked about confidence intervals, hypothesis tests, talked about confidence intervals and hypothesis tests for multi-sample data, and then we've looked at simple linear regression. We've covered everything at sort of an extremely high level and sort of given you a taste for all of these different subjects. All of them go much deeper than what we've had the time to discuss through the course so far, but hopefully you're starting to see how all of these pieces come together, how we can try to do the process of estimation or inference, and in order to do so, we're going to make use of probability tools, right? And so we need to sort of have all of these working in conjunction with one another. But with all of that, that was what we wanted to cover throughout the term. So I'd like to thank you all for watching these lessons. I hope that this has all made sense, and I'm looking forward to getting to finalize the course with you all.